Connor emailed me, said he won't be here, but Ian should be here in a bit. So there's another structure of adder. It's called carry look-ahead adder. And there are many other types of adders structures, but I think I won't be able to have the time to introduce all of them. So just introduce another one instead of the one we talked about in the past few weeks. Do you know the name of the last one we introduced to you guys? Yeah, it's called repo carry full adder. Because the carry migrates to the MSB, so it's like a repo. It's called repo carry full adder. For this one, okay. It has all the S and C's. So for this one, for the carry look ahead full adder, it's being derived in a different way, but still using the same logic. So the advantage of using this one is you can get C2 a little bit faster than the repo carry full adder. You can see here, you won't get C2 until you have C1 available here, right? The C1 is being used as in one of the inputs for this last stage. So it takes relatively longer time to get a C2 compared to other structures. However, since we know the logic, there might be an opportunity that we can probably try to find C2 a little bit sooner to make the adder slightly faster than the repo carry full adder. I'm going to show you a simulation, and this will be homework 5 for you guys to build this one and the carry look ahead adder in LT-Spice. The reason I want you guys to use LT-Spice individually instead of using electric VSI is because it's a different design environment. In the future, a lot of times you are not necessarily making a layout. You may just want a schematic to verify a logic or a circuit design. So you may need to know how to design symbols and the different structures and layers in LT-Spice. So for homework 5, please not use electric VSI. Just come back to LT-Spice, building all the circuits over here. And our course project is also based on LT-Spice. So we don't have the time to lay that out. So it's going to be built in LT-Spice. For the logic for carry look ahead adder, it's not changing the full adder's nature. It's still a full adder, so the logic is the same. S equals A, XOR B, XOR CI, right? For CL, it is A, B, or A or B, and the CI. And we're using, so we renamed this term as the generate bit, or bit G. And this term is called the propagate. And you'll see Y in the bit, okay? And or bit P. This is very simple, right? It's just simply A, B, C, I. You have XOR gate here, output, and okay. So for this S, for the summation here, it's very simple to design the circuit. But for the CL, we are doing it in a different way. Okay, so C out can be rewritten as G or PCI. Okay, P or PCI, because this is a generate bit and this is a propagate bit. Okay, so for C1, so here's, for example, we name it C minus 1. This is C0, C1. For C0, it equals G0 or P0 and C minus 1. C minus 1 is a carry in. We just name it as C minus 1. It's my way to do it. So P0 will be A0 or B0, and A0 and B0 will be G0. Okay, so C1 is G1 or P1 and C0. Right? Because C0 is a carry in for C1 to get C1. Still using the same logic equation here. I'm substituting the Ci, which is the carry in, using the exact carry in being used for that stage. So C2 becomes what? G2 or P2. So what is G2? What is G2? So I'm going to show you what is G0. So G0 is simply A0 and B0. Because G is A and B, right? In general. So G0 is A0 and B0. So G1 is A1, B1. G2 is A2, B2. Okay, so C2 here becomes G2 or P2 and C what? We're looking at here. So I'm going to substitute these C's using the previous C, and we can find out the final equation for C2. Okay, so C0, we're not changing it because that's the initial input over here, initial carry in for the entire circuit. But for C1 can be rewritten as G1 or P1, and you just substitute C0 here. Okay, it becomes G0 or P0 C minus 1. Okay, and C2 becomes G2 is not being changed because we know it's A2 and B2, or P2, which is A2 or B2. Okay, and then we substitute the C1 from here. So C1 now becomes this. And we can expand this term plus P to G1 or P to P1 G0 or P2 P1 P0 C minus 1. Oh, is that G0? Oh yeah, it is G0. All right. So that's the final result for C2 or logic equation for C2. Let me double check. P2 G1, P2 P1 G0. Yeah, that is correct. Okay, now you know the logic equation, and you can just use the logic gates in your device and to build this circuit and compare if this one can get C2 a little bit faster than the ripple carrier flighter. So we need to build the ripple carrier flighter in LT Spice as well. So what I will do is having all the logic gates available, like XOR and OR gates available in one folder, so you can reuse them when you build this one, right? And then you have one FA, it's a 1-bit FA in your folder, and then you start another schematic, so you can reuse the FA in that schematic. So you can just place 3 of them in the schematic and make the connections and do simulation in that schematic. Okay, so I'm going to show you some expected results over here. Okay, so task 1, by the way, this is a 1-week homework. Okay, so it takes a week, so it's due next Friday. Derive the logic functions of the carrier lookup adder. I already did that for you, 20 points. Okay, as a gift for you guys. Task 2, build a ripple carrier flighter and a carrier lookup flighter in LT Spice, not in electrical VLSI. Another 20 points. So it look like this. Okay, so I have the LSB on the left-hand side, but you can do whatever we have been doing, right? So keep the MSB on the left and carry in from the right. But it's going to be equivalent electrical-wise. Set up some of the power supplies. And because the goal is to compare them, and definitely we are not able to compare every single logic of it. And this is a carrier lookup adder. So if you zoom in, you can see the signals are on the top. Oh, it's not very clear right now. Let me see. Oh, here's clear version of it. You'll see A0, B0, that's a G0 term, and A0 or B0 is a P0 term. So you make all the G's and P's available here. So why it's a little bit faster than the ripple carrier flighter? By looking at these G and P's, you see that because all the A's and B's are available. These are inputs to the adder. We know they are there, right? We don't have to wait. They're inputs, okay? So since A and B's are available at the very beginning, and we can directly find out G and P's by just passing these inputs through one gate instead of multiple stages. So the delay from A's and B's to G's and P's is just one gate level, or just one stage delay. Okay, but now let's come back to look at the equation for C2 over here. What are the terms we have in C2? G's and P's. Are G's and P's available at the very beginning? Yes. Just one stage of delay, right? Because all the A's and B's are available. All the A's and B's are available. So it's just through one delay, one gate delay, then we are able to get a G's and P's. Do we have anything else over here that we may need some more delay? So if we come back to the ripple carrier flighter, okay, from here, the inputs to here, especially for C2, it takes so many stages. It's definitely not 1, not 2, not 3. It's probably, I don't know, every flighter has maybe 2 or 3 stages. So it's about like 5 to 10 stages of delay from here to here to get C2. However, in the carrier look-ahead flighter, if you look at C2, C2 is simply just the signals from the first stage. But also you have more gates over here, right, to get the final C2. But still, the logic to get C2 is from A's and B's, and you can get A and B's into GNPs using this equation, so it's given. So you don't have to wait too much. And if you look at the results, definitely it's not that perfect, right? But if you look at the results, it's actually a little bit faster than the ripple carrier flow adder. So how do you find out it's faster? I used, I think, 111 as A and 00 something for B. And I think I toggled this LSB for B because to get C2, you just need to get a carry out from these two numbers, right? So if I have a 111, you just need to add a 1 here, then you got a C2. You know, is that making sense? So 111, if you look at on paper, 111 and 00 something, right? If this one becomes 1, you got a C2 as a 1, right? If this one is 0, if this one is 0, like 111 plus 000, there's no carry out, still 0. It's not changing. So if you toggle this bit, you are able to toggle C2. Okay, you're able to toggle C2. C2 will be toggled. So in that case, you can see when C2 arrives, because they have edges, they can compare the two graphs using the carry look ahead flow adder and the ripple carry flow adder. They can compare the time when you get this edge or get the C2 to be toggled. See which one will happen earlier. Okay, so that's a strategy to verify that the carry look ahead flow adder is a little bit faster than the other one. And if you compare these two graphs, do you think it's a little bit faster or not? What are you looking at? Which one's faster? So where's C2? On top, yeah. So is it faster? And can you tell? Really? From where? Wait, it's later or earlier? Earlier or later? Yeah. Because you can see that. So first we compare to C1. It's not probably not the one you want to compare only to. But you can see C2's edge, rising edge is over here, right? It's changing over here. It's already very close to the saturated voltage of C1, right? Happens a little bit late, but this one is earlier than this point here, right? And also if you compare to S2 or S2, yes, because the final result consists C2, S2, S1, S0. That's a 4-bit result, right? And if S2 is already available, which means S1, S0s are also available, you just need C2 to compile the 4 digits into 1, make the final result, right? So you can compare C2 to S2, see which one, see if they're close to each other. You know what I'm saying? Because C2 is always the latest you can get, right? So it has the most delay. However, S2 is the second delayed, most delayed. So if you get S2, which means S1 and S0 are also ready, we're just waiting for C2, okay? But it probably cannot improve anything about S2 anymore, okay? So S2 is already here. But in the ripple carrier flow adder, you can see that C2 is probably, you're getting C2 at the same time as S2, okay? So it's not that significant because you are getting C2 almost the same time as S2. So I was hoping this is delayed a little bit more, right? So then that makes a lot of sense. It's more significant. But now it seems like S2, you are getting S2 at a later time, almost the same time as C2, right? But for the carry look ahead flatter, C2 is earlier, happens earlier than S2. So C2 is right there before we get S2. It's not hurting anything, it's just better, right? It's just making things better. Who knows? Sometimes you get different digits. Maybe S2 will get delayed. But I think if you draw a line here, I think C2 is slightly later than S2 for the edge to be changed, right? So it's not helping anything, right? But here it definitely helps because C2 happens earlier than S2. Okay, if you can show similar graphs like this, I think that should be task 3, I'm sorry. So the task 3 should be completed. Explain why CLA is faster. CLA is a carry look ahead adder. Okay. Explain why this is faster than the ripple carry adder. So build a circuit in lec27 and run a simulation and verify that this is a little bit faster than the first one. Okay, that's homework 5. Next Friday.
Are there ones that we can use built in this place, or should we use the ones that we built?
Use the ones you build. Don't use the ones in lec27.
Will it cause issues? Because I'm not sure. Like, I remember when I did it in Logic, I don't think I put like the transistors in the most efficient way. I think I like built the AND gate from NOR gate or something like that.
Yeah. Don't do that. If you look at these examples here, just do whatever I did over here. Okay, starting from transistor level circuits. You got a V high, V low. Okay, as ports because they need to be powered up and grounded. That's 3 inputs, 1 output. And similar for the 2, like AND, right? So for the AND gate, you need a NAND gate and 1 inverter here. It should be easier this time because you have learned all the stick diagrams and the circuits. You know where to connect instead of connect to any of the random ports in logic. I see all the weird connections into the circuits in logic because they didn't know what's going on in the circuit. But now you know.
Are these examples available, or should you just use
Oh, you don't need a stick diagram. Stick diagram is for layout. This is just for schematic, right? So you need to draw the shape here in lec27 instead of in electro VSI. Just to learn how to do it over here as well. The course project will be a large scale schematic circuit in lec27. And okay, so build individual gates, including the inverter. Sometimes you need an inverter. You have to build an inverter as well. NAND, NOR, right? Or you build it one time, you can use it for multiple assignments in the future. Okay. Any questions for this schematic? No? Okay. I'll give you guys a review on flip-flops. So I'm going to use the flip-flops for control circuits in ADC design at a later time. So I have to start from latches. Circuit. And the name of the latch is called SR latch. The schematic looks like this. Feedback, input, and Q naught. And most of the time, so S and R means set and reset, right? the set and reset latch. It's quite useful circuit. So just based on this drawing, I know this is Q naught, and set and reset is actually setting and resetting Q. So setting means you give Q a 1, so put a Q on 1. And for reset, you give a Q a 0. That's called reset. So we are always talking about Q, not Q naught. So in that case, if this is given, right, which terminal should be S, which terminal should be R, and why? For example, S and R, okay? And for the input of S and R, and for the correct use of, for example, you got a circuit, you have a user manual, right? So we only give 1, 0, 0, 0, 1, so the two inputs. If we want to hold it in the memory state, we give, for memory, I'm going to let you guys find out later, okay? And also there's a state that are not being used. Sometimes other instructors may tell you that that's illegal for as inputs for the latch, which scares you. Why is it illegal? Why you cannot do it? It's just a circuit, apply voltage, something will happen, right? A lot of times it makes you feel like it's super uncomfortable to see that kind of input for the latch, and you just don't know why. It's just the voltage. Okay, you apply a voltage, something happened. We just don't use that voltage. Nothing serious. Okay, so now let's look at the normal operation states like 0, 1, 1, 0. For example, SR, RS, whatever. So for this, if we name this pin as S, this pin as R, okay? So we're assuming that if we turn this on, which means we give a 1, we are setting the Q. Remember, so you turn it on, which means you give a 1 to it, which means you are trying to set Q. You turn on S, you give a 1 to S, same thing, okay? You turn on S, you give a 1 to S, and you are setting Q. Okay? Since this is a normal operation, if you give a 1 to S, you must give a 0 to R. And now we get the inputs for the circuit. Let's verify if Q is 1 or not. There's a little feedback circuit. That's a NAND gate. Since we don't know what is this signal or voltage on the feedback loop, so if we just give a 1 to one of the inputs of the NAND gate, can we determine the result or the output? Are we getting a definitive output over here or not? If you give a 1, so what is NAND gate? A, B, okay? If one of the input is 1, do we know what's going to happen? No, it just be 0. It all totally depends on B. So this guy cannot tell anything, okay? When you look at AND gate, NAND gate, you have to look at 0 because 0 is going to set the output for the NAND gate. With 0 and everything will be 0, and then it's getting inverted for the NAND gate. So definitely you're getting a 1 here for sure. If you give a 0 for one of the inputs for the NAND gate. So 1 will be fed back to here, okay? And now it's 1, 1 NAND. What is it? 0. Are you setting Q? You are resetting Q. So if you turn on this pin or this wire, you are resetting Q. So this pin must be reset, not set. Okay, if you keep Q on the top as the output, keep in mind it's RS instead of SR. Okay, it's RS from top to bottom. It's RS for the input. Now you'll see a SR latch using NOR gates instead of NAND gates. Specs is doing the same thing, but R and S probably will be swapped. But now let's verify. Okay, anyone can verify it for me instead of me doing everything? This is Friday.
So for the top one, if S is 1, if talking to S and it's 1, that output from that to Q is always going to be 0.
Mm-hmm. So 0 will?
Or, yeah, 0 will go down.
Mm-hmm. Yeah, so it's going to be reset, but let's finish it first. Okay, got a 0 here, then what's going to happen?
So R has to be 0.
Mm-hmm.
So that.
Mm-hmm. So got a 1 being fed back. Mm-hmm. It's not changing anything.
Yeah.
Okay. So is that S or R? Yeah, still R. So you don't have to swap it, right? Because R, when you turn on R, which means you give a 1 to R, you turn it down, and now you're resetting Q. It's like exactly what we expected.
Is there a way to swap it? If you like use just regular
I don't know if you should use an AND gate. Oh, if you add another stage, you have to swap it later. It's called flip-flop. So it's another stage adding to the latch, it makes it into a flip-flop. So we're going to cover that in a bit. So, but if you use just NAND gate NOR gate, so actually they are not being swapped. It's always RS. Easier to remember actually, which is good. So that's 0 or 0, 1 or 1, 0 state. So what if you have 1, 1 here? What's going to happen? It's not illegal. It's a memory actually, yes. Why is the memory? Because one, like what I said right here, right? One and anything is still that thing. So it's not changing the input. So whatever it used to be, for example, it has 1 and 0, right, as a digital signal. And another clock cycle, it keeps at 1, but this one toggle to 1. Okay. So during this time frame, you have a 1, 0, okay, for example, 0, 1. So during this time frame, it was 1, 0, okay? What happened to the result, to the output? If you have 1, 0 for S and R and S. Okay, so we're getting 0, 1, right? Okay, now another clock cycle, it moves to 1, 1. This one toggled, got toggled. You got 1, 1. So what's going to happen? Stay the same. So it's a memory. It's not changing anything anymore, okay? Because you got 2 1s, and you got a feedback signal. For example, it was 0, 1 as a feedback, right? So 1 will be fed back here, and 0. So it doesn't matter because 1 is not changing it because it was stable. It was stable. Electrons are moving super fast, so it's already stable here. Okay, and then you change it to 1, 1. So 1, 1 and anything, still that thing. It's not changing anything. Just a memory. But when you use a NAND gate structure, if you have a 0, 0, sometimes they'll say it's legal, it's not being used. Sounds like you are going to burn something in the circuit, but actually it's not. What's going to happen? Or will that confuse the latch? The latch doesn't really mind. What's going to happen if you have 0, 0 here? So 0 is going to, sometimes it's kill. It's going to kill that NAND gate and give you what? 1, 1 for the output, right? So for example, if we have 0, 0 here, okay, And no matter what the input for the other terminal is, it's going to directly kill the NAND gate and give you 1, 1. Okay. And 1 will be fed back to here, and 1 will be fed back to here. So it's basically one NAND gate has 0, 1 NAND together. You're getting a 1 still. It's not changing, right? And here is also 0, 1. It's been NAND, and you're getting a 1 as well. And it's actually stable. It's not oscillating. But you are just getting 1, 1 for Q and Q naught. But because we defined the latch, the output here as a Q, we name it as Q, here name it as Q naught, but eventually you got the same result. Sounds like embarrassing. Right? So it's not going to do anything to the circuit. It's just giving you two results not being used at all. A lot of times we use a latch because we want to use both the Q and Q naught output for a certain purpose, right? But now it's not Q naught anymore, so it's that same signal will disable a lot of functionality of the.
So would you ever use the memory setting?
Oh, the memory is being used a lot, but the unused, for example, 00 for the NAND gate latch is not being used. It's just called unused.
So as a memory state.
Yeah. So for memory state, what are the SNRs? Here. Okay. So for the NOR gate latch, you can have 1001, right? The states, and for memory and unused, they can be slightly different. Which one is the memory state? Yeah, zeros are memory because zero is not affecting the OR logic. So 0 or something is still that thing, right? No. Yeah. Thank you. Okay, so we got a 00 for the memory state for SNR because 0 is not affecting the result of the OR gate. Yeah, 1 will put 2 zeros over here, okay, no matter what the previous signal was. Okay, so that's the SR latch. It's not just being used as a memory cell a lot of times, but also, for a debounce circuit, you have using a debounce technique in software, right? Adding a little delay in there to debounce it. But you can also do a hardware debounce by using a latch. Debounce, which means you press the push button, like push button in a circuit. And it's a mechanical system, it varies a lot. So it's actually not directly turning the on or off, right? Like that. It's actually vibrating a lot, like this, and until it's getting stable. This happens really fast, probably 100 milliseconds or even less. But making it difficult for the software to detect the signal because you are trying to see when, for example, you have an if statement, right? If, for example, if you push it, you're expecting a high signal. This is whatever you expected. This is whatever happened in the circuit. You're expecting it will make a solid touch whenever you push it. So it's just to make a super simple if statement in C++. If the logic is high, I'm going to do this, all right? But however, it's like this, really fast in the very beginning, okay? Maybe 10 milliseconds, let's make it shorter. So, but the software can run really fast because your Arduino is running at 160 megahertz or 60, I forgot, 60 megahertz or 160, probably 16 megahertz. So it's running at 16 megahertz. So the software runs a loop within like microsecond level. So in that case, it detects if the voltage is high, you do something, and then the voltage becomes low really quickly. So you're actually making it super inaccurate for the software, because software can run really fast. And you want to have a time delay, right? You press it, you detect a change, then you start a timer, okay, until a certain time delay, you detect that again. If it's still high, which means somebody really pushed the push button, then we'll just execute the following code over there. So the debounce. So you can do debounce by adding a time delay to C++, okay? But also you can use a latch to debounce it. I'm not drawing the circuit here for you because I forgot how to draw it. Yes, if you don't want to use the software to do it, you can also use the hardware to do it. It works pretty well. A lot of times the circuit doesn't have a CPU, right, running all the code. Probably it's just a very simple circuit. And then there's nowhere that I can write that script, right? The only way you can do it is just adding a, passive circuit in there, just logic gates. So SR flip-flops will be the next step. SR flip-flops. If we keep using that NAND gate structure, it looks like this, which is adding one clock stage in front of the latch. That's the input, and that's clock. Now I'll let you tell me which is R, which is S. Okay, in this schematic. Okay, let's try if that works. Okay. If clock is 0, what's going to happen? And 1 is doing what for the latch? Memory. Okay. So when the clock is just toggling from 0 to 1, 1 to 0, right? Okay, so when clock is 1, it enables it. It's not affecting anything because 1 goes into the NAND gate, still that thing, still passing R and S to it, to the next stage. It's not changing anything. The clock is not really changing too much to the input. However, if you have a 0, it memorizes the previous state. Okay, so this will be memory. Because when clock is 0, it's not doing anything, so we just directly ignore it for now. We will not analyze the logic. Yeah. Then what's going to happen? That's right. That's what I'm trying to say. Okay. Do you all agree with that? Because performs like an inverter, you see a bubble here is going to invert everything. Okay. So it used to be RS, and now it needs to be SR. And is this a level trigger flip-flop or edge trigger flip-flop? Which means if clock is 1, is it going to pass changes of R and S to the output? Yes. If you put a clock on 1, all the channels are open, right? Whatever SR changes is going to pass to Q. Is that good or not? Huh? How you use it? Yeah, that's right. Yeah, you consider the cost and everything, but ideally it's not a good design, right? Because when you have to toggle your clock really quickly, and also it's not really resistant to noises. If the S and R get changed, and at the same time your clock is on, because always, and most of the time the clock will be on for a while, right? And during that time frame, your Q, your output will be changed, will likely be changed at the same time when S and R being affected by any of the noises. Yeah, you want it only happens at the edge. If it only happens at the edge, because the edge is sharp or very narrow, right, very fast. So if it only changes or only send the signal from here to the output at the edge, Then after the edge, you get on or off, doesn't matter, okay? So it's gonna, so the output won't follow the input, then that would be ideal. But this one is very simple flip-flop, only do a level trigger, it's called level triggered. Flip-flop. And this is called the SR flip-flop. And you can make this one into a D flip-flop really quickly. And D flip-flop will be the one being used a lot in digital circuits. So D flip-flop is a data flip-flop. Instead of having two inputs, it only has one. So simply connect these two inputs using the inverter. Okay. And you name this one as D. And now we have to verify because it's a data flip-flop, we are not supposed to invert it. So D, the data will be the Q after the clock is enabled. So now let's verify if we are getting D here at Q. If the input is D, are we getting a Q as D, the same as D? Because data, right? Data will be passed through.
Yeah. D is 1, then D set.
Since we have S here, right? This is S. Okay. So we know if D is 1, we set it. If D is 0, we reset it. Okay. And the reason we put an inverter here is because remember the states when we use it. Okay, the inputs are inverse, right? If one, the other one has to be 0. If one is 0, the other one has to be 1. So that's why we just lock it in that state, the two states. So you're never getting like both zeros and both ones. It's not really memorizing by the inputs, but it's memorizing using the clock, right? How's that useful? Yes, passing data through, because sometimes you don't want to, the data is still changing, it's not ready to be sent out to the output yet. You want to wait for a couple of cycles. When it's ready, it's like a door, right? Whenever it's done, you open the door and send the data out. The clock just add a delay. The clock is like a command, right? When it's ready, you send it out.
So like the purpose of this portion of the circuit
Mhm. Is to add a control circuit, a control signal, or add a command signal here. If you don't have this state, it's just a one passive gate. Nothing can control it.
so
Whatever.
So it's easy to turn it on.
Yeah, yeah. Okay. And also you can use these. So definitely you can replace this one with the NOR gate latch. Okay, but still using this NAND gate clock stage, which is working a slightly different way. But a lot of times people just prefer NAND gates, probably because it's, I mean, if you look at the circuit, I think it's adding, because PMOSes are slower than NMOSes, and if you put the two PMOSes in series on the top, it's adding a lot of resistance to the PMOSes, making it more slower, even slower. I don't know if that's the reason for that, I forgot, but you need to know that a lot of times we prefer NAND gate. And you can just build a digital circuit just using NAND gate, but instead of any other circuits. Because it is able to, you can use NAND gate to make everything.
Yeah.
Interesting. Yeah, faster than NOR gate, yes. You can also build everything using NOR gates. So, it forms a NAND gate, NAND logic. You can form a OR logic, AND logic, just invert it, or you short. If you short the two inputs together, it's an inverter, right? So basically, you can build anything. You can build a CPU just out of NAND gates.
most
Is that because the holes are, let's see. So one of the reasons is probably the threshold voltage is higher. So whenever it starts from 0 to high, right? At 0.8 volts, NMOS is already on. But for PMOS, it has to wait for another 0.1 volts rising time because PMOS are higher threshold voltage. And why threshold voltage for PMOS is higher is because holes have a lower mobility compared to electrons. And you use electrons to form the channel for the NMOS, right? And it moves faster, but you are actually forming a channel for PMOS using holes, which moves slower. But the holes are not moving. These holes are just the positions, like vacant positions.
I think I mentioned that often.
They do move?
Yeah.
Relatively.
It's like a weird quantum thing.
Okay. But do they just move a little bit, or they move for current? Okay.
Unless I misunderstood.
Yeah.
But he said it was like a weird physics thing.
Mm.
That's
Okay. Okay. Yeah. Well, luckily, we're not physicists.
Yeah.
We just get a circuit design and and receive that 100K from the company. We're done. They just go out for hiking or camping. All right. It's pretty much the entire class. I think I have a few other simulations I want to run probably next week. Okay. All right. We'll see you next week.